So I have the good fortune of reporting a lot of different information to you that probably you've never seen. It hasn't been published. It hasn't been put out in the public. And the reason was I used to be the vice president of research for a company by the name of Inco. And we produced at the time about 20% of the world's nickel. And I had a guy come into my office one day who was the vice president. And he said to me, I have a huge problem and you need to help me with it. And since you manage R&D, this will be your challenge. The problem was that he would get people to 200 feet or 400 feet or 600 feet underground and he couldn't move them again. So he asked me to invent the Star Trek transport. I'd just like to beam that guy from this place to get him to do that work because he only ever goes there for about 10 minutes. Or half an hour or something, and I lose so much of my shift. And taking him down underground and getting him into the place, sometimes he can get a mile or two away from his entry access point. And so, as we went forward, we began a project which was on teleoperated mining. And the idea behind it was to use the best of teleoperation and the best of autonomous systems to allow us to create industrial robots as fast as we could so that we can put this kind of system in place. I'm going to show you the results of that, but I also want to put it in the context of this. 3 years ago, the Canadian Space Agency came to me and asked me to take a look at how we might build a mine on the moon. And the reason for that is Canada right today has probably the vast majority of mining experience around the world. Between us and the Scandinavians, we know how to mine and we know what to do. And so I took on the challenge of creating that document. I got Brad Blair to help me and a few others, and we put together a team of people that would do that. And so I'm going to show you part of the results of that today, which are mainly the mining system results. And then tomorrow I'm going to show you some of the scenarios we put together with some of the technology ideas that we had. This was the base case for what we were looking at. And there's a couple of things in there that I would argue quite vehemently about that I don't think that in the long term this kind of thing is really going to be possible. One of the main reasons is that radiation will cause a tremendous amount of problems for people. And the other one is that if you do go to really mine, and I want to show you a little bit about underground mining and looking for concentrations in these materials, to be profitable, we're going to have to find large concentrations of materials, not small. And with the transportation costs that everybody's talking about, this stuff is great for an initial exploration piece, but as we move into the future, it's going to have to get a lot more serious. One of the things that we looked at in our study was looking at the impact of cosmic radiation. And we had a number of papers, both from NASA and around the world, that basically said that cosmic radiation was really the showstopper. That would be the reason that people would have the most problems in what they were doing. As well, 80 centimeters of regolith maximizes the production of secondary radiation problems versus surface exposure. And so we had to get below that 80 centimeter depth. So we would need at least 2 meters of coverage to be able to do that. Now, coming from an underground mine where I construct underground facilities all over the world, it seemed to make a lot of sense to look at putting people underground. Otherwise, you have to transport large quantities of water to protect people. And so we started to investigate what it meant to go underground on the moon and create a base. This slide is an overall concept slide about what we have been thought would be the most reasonable way to approach it. The ideas we had is that we had already been able to look at building these kinds of facilities, and I'll show you some videos of stuff that already exists in the field where people are running mines like that around the world. It's not just a research project anymore. There's companies in Chile, there's companies in Africa, there's companies in Australia, and they're all doing this work because this is the most suitable way to get the safety results that they want and reduce the cost of materials. And then we looked at what you could do with underground facilities, putting proper airlocks in, creating really only about 4 pieces of equipment that would need to go to the moon to be able to continuously build a habitat that could grow with people as they came. Now I'm showing you this is going to take a second before it starts, but I'm showing you this because it's either we do what's about to happen on the screen, or we have to deal with gravity in a very different way than probably what most people are used to. Mechanical cutting of rock requires gravity, and it requires a lot of gravity to be able to do it on a large scale, unless you want to do this. That blast that you see there went off last week. That blast was a total of 72 pounds of explosives, and it made an opening that was 10 feet wide by 8 foot high by 6 foot deep. That's all it was. In our business, we regularly let off millions of pounds of explosives at the same time to be able to mine. That's what open pit mining is really about. Being able to break up material on a large scale and then take that stuff and make it smaller and get the value out of it and process it. The one thing I haven't really heard a lot about is concentration yet of the resources that you're looking at. You know, we don't work in parts per million or parts per billion. We work in percentages that are in the order of 2 to 3 and sometimes 40 and 50% of the rock being the materials we're trying to get. That's what pays on Earth without all the transportation costs to go to the moon or go to any other planet. I want to just talk for 1 minute so that everybody sees this, because most people don't really know what a mine is. And if you look at this concentration here, that's what we tend to look for, things in concentration. And usually those things are done with exploration drills. They usually start as an open pit, although we're having more and more trouble putting open pits in place because society doesn't like them as much. But we still do them. And then we put head frames in to be able to get material in and out, and we break this material with explosives. We bring that material out. There's some new techniques which I'll show you that are a huge advantage in the world. And most of the biggest mining companies in the world are beginning to use them. To give you an idea of design to production, though, this is a video from a little ways back that I created so that people would begin to understand what we do. We usually sink drill holes and we look for these areas where we intersect the material. Once we intersect the material, we connect up the dots in an intelligent way. I don't want to say it in any other way than that, because there's a lot of geologists that work very hard and understand how to do that. Once they do that, they get an ore body outline, and we begin to look at how we access it, and we continue to drill it to find out whether we're moving out the good stuff or the bad stuff. Now I wanted to show you a couple of things that will be interesting to you. Like I said, a lot of the work we did was very secretive inside the company. This truck that you're about to see was built in 1992. It went into production in 1992 and was constructed in the late 80s. It's an automatic guided vehicle that's been put in place. It loads by teleoperation. where the operator sits around the corner in a camera, using a camera. And this machine is a 70-ton vehicle that hauls a 70-ton payload. It was in production for 3 years and moved 2 million tons of material by 1993. I showed that at a talk at MIT because they were just beginning the Darwin challenges around 2004. And they were completely amazed that the mining industry had done that and nobody knew about it. And we had been working on this for a long time. And this particular truck, although it's working on the level here, is capable of pulling a 25% grade. That's very important for underground miners because it minimizes the amount of tunnels we have to build to be able to get the material out of the ground. We started off with this idea around the time of that truck, which spawned the idea of creating teleoperation centers for running mining operations. This was a graphic put together in 1992, and we put it together to try and show our senior management what the mine of the future would look like. All flat screens. The dates it, right? But that's the kind of systems that I had the opportunity to build over the last decade and a half. So we coined a term which we call telemining. In our business, a lot of people didn't get the idea of teleoperation, so we started looking at things that they would get, and we came up with the television and the telephone, and we said, so telemining. The idea was really to apply the best in information technology to be able to allow people to run machines terrestrially, and now with what we're looking at here, extraterrestrially. I put up this video because I want you to understand the scale of mining, and I want you to understand the kind of machines that are used. This area here is an ore body in a mountain range. We usually access the ore body through some kind of tunnel system, and then we build a lot of underground workings underneath it. In the total amount of work, there's only about 4 or 5 pieces of equipment that we need to be able to accomplish that task. In this particular case, this type of mining requires no explosives, because you'll see. In this particular case, this type of mining requires no explosives, because you'll see in a minute that as you create these herringbones with these few pieces of equipment, a robot that drills a pair of robot arms, usually about 70 holes. Then a group of people that come in and load it with explosives. And I was at an explosives maker last week who's now working on explosives who would put in the holes so they don't have to be wired, they'll just be automatically put into the hole. They'll know exactly where they are in 3-dimensional space, and they'll break the material and pull that out. This is really, really standard stuff that goes on all over the world every day today. Once we do that, we come back in and we support it up. And you'll see in a second, as we begin to do this, this upper orange level goes in and we begin to undercut. And I want to make the point that mining on the moon is going to require gravity. Today, Earth's gravity allows us to understand how to undercut that and what the dimensions are. Leslie and I have been working on a proposal that went into the National Science Foundation to take a look at what it would take to do that same kind of mining on the moon at 1/6 gravity. Because that's a very difficult thing to do, and miners use gravity to their advantage every day. So gravity changes are a huge problem when it comes to mining, because you need to understand very well. What this machine is doing is creating a draw point that allows material to feed to it by gravity. And so you'll see in a second that they'll drill the holes and then they'll load them with explosives, and we'll begin to create a funnel, a solid rock funnel that all the material goes into to be able to load trucks and trains. These kind of machines will go in and dig them out because that rock will swell to 35% greater than the size of the material that's in situ because air voids go into it. And then you'll see we drill holes up inside and then we blast it all out. That hasn't changed for a long time, other than now we can do that with tele-remote equipment. The only reason that we use tele-remote equipment is because we have not figured out completely how to make an autonomous system work in a non-homogeneous material. So if you were to think of being on a CNC machine with metal, that's pretty homogeneous material. This rock has joints and fractures in it no matter where you go, whether it's on Earth or the moon, and it will be hard, and people will have to be able to look at it and understand what they're doing. These machines work pulling out material from those drop lines. This particular style of mine, you'll see a mine go in place for in the order of 50 to 100 years. There's a mine in Freeport called Freeport-McMoran down around the equator. It's been running for a long time, will continue to. There's another mine up in northern Sweden called LKAB. It's been running continuously since 1750. And it uses exactly, well, not exactly, but a similar method to the method I'm showing you here. These become very important because on the scale of the world, this is how you get all your raw materials. And when we go to the moon, or when we go to Mars, eventually we're going to have to do this if we want to sustain life up there. Because this is the only way you're going to get the raw materials to do any of the manufacturing that you guys are talking about here today. So telemining does a couple of things. One, it puts people in safe locations. It keeps them on surface and they don't have to go into the operation. We do put vehicle guidance systems on machines. We have typically, because we have to maintain the machines, provided an external guidance system so that we can have access to the guidance system for people to enter the workings. Key technologies for this are telecommunications networks, positioning and navigation systems, and then looking at our methods and process control. This piece of work is what I got my doctorate for, which was building a 800 megabit per second underground network to be able to run mining machines so we could do this on a consistent basis with video cameras on every machine. This is the system installed. It's very simple. We're working on broadband technology with the guys at MIT when they first started looking at broadband technology back at the beginning of my career. We also use some pretty interesting technology to be able to use non-GPS because GPS does not go through rock. And so we've been very good at getting inertial systems that allow you to do the work that we need to do. This is one of the projects that we produce, and it goes into business every day. We put this unit of ring laser gyro together with a scanner and put it on a machine. And this is a unit that's surveying an underground tunnel and getting the information together for people to be able to generate these kind of maps. This is a 2-kilometer long survey that's gone and gotten a completely reconstructed environment that you can see some of the things we have to deal with, things like ventilation tubes and others. I want to show you one last thing before I close. This is a machine that we did for looking at how you would build an exploration machine that would go in. It's a completely automated machine that will drill up to 1,000-foot holes to probe into the rock. And we took and built this machine mainly because people were getting their fingers cut off. That's the kind of environment that diamond drilling is. Mainly because people were getting their fingers cut off. That's the kind of environment that diamond drilling is. This is probably the most important piece. When we create tunnels, you saw that jumbo. This is a teleoperated jumbo, 4 camera views. But what we did was we stole a video game airplane controller and put that Porta and the other unit and the other scanning material into it. This unit was the first time that we'd ever had an avionics system fly a piece of mining equipment into the face. And now we have technology that we're working on, which I'll show you tomorrow at lunch, where people will be able to get not only this kind of inertial position, but an absolute position using a new kind of GPS system that we've invented. So with that, I'll close and I'll give you some more information tomorrow at lunch about what we put together for the CSA, so you see the kind of concepts we have and what we're doing.